lots of low back support, something on the chair, radars on the chair, that's on the that is more of that I have. Within this row is going to be standing at that. Okay, X-76, helicopter and a hover with autopilot and SAS on a little arm. Has limited authority SAS limited to about 10 or 15%, which is about an inch or inch and a half of equivalent cycle W. A series actuators back there, lengthening and shortening the control room from the stick out to the spot. And you can make that out as much flow as you want. A typical number will stop that is 10 or 15%. The trade-off there is the time of failure. And that thing moves, it will be moving like less moving the stick an inch or an inch and a half behind the scene. And so that's how much response you get to a failure. And most people just think about the actual itself part of it, which can happen. Right? But the thing about a SAS is it's got really three basic components that the actuator. And it has a computer, and it has a sensor, like it's for damping, and it has range gyros. Whatever sensing that you're feeding back can also harm. I can have a range gyro, all of a sudden something happens to the gyro, and it says you're rolling at 100 degrees per second. Well, SAS is going to try to oppose that. So it wouldn't necessarily be actuated that part of it. In that case, it goes easy to sensor. So the trade is, I want to be able to have some stability, augmentation, but as we look at some of the other parts of the question, I only really need it around small altitudes, let's say roll or pitch. Because if I'm doing a big, rapid roll rate or big pitch rate, I'm doing that because I'm rapidly trying to change the flight condition of the helicopter. Okay? Whereas when I'm trying to do something very precise, my rate is really low. So I only really use the augmentation about a small portion, not some. Talk more about that. Okay, you do autopilot controls the cycle controls in the cockpit. Okay, so autopilots move the controls 100% ability. Right, if I'm really, really slow, and I can overcome it, and you can see it happen. The autopilot's moving the stick. If your hands aren't on it, you'll see it. If your hands are on it, then you'll feel the forces go up. Right, so you have a clue that's happening, and you can overcome it, don't go very fast. SASs are happening behind the scenes. Most helicopters do not have. Some do, some don't. Most don't have gauge as to where the SAS is. Let the wing stand in. In the instrumented 72, we will have the seamless. The seamless position will be displayed on the instrumentation. Most aircraft don't have it in the design. So it's happening behind the scenes, and they can move really fast. SASs are like super high frequency. Okay. You got step inputs and pedals, longitudinal and lateral cycles of everyone. Part A. How do you expect time constants for the responses in pitch and roll and not prepare? In other words, here's the one where we're saying I can use that short-term approximation for all three axes, whereas the steady-state rate, which could be roll rate, pitch rate, or yaw rate, is going to be, the words are minus sensitivity times input divided by damping. And you have the appropriate dampings and sensitivity out of that suit. But damping for roll is LP, and we'll talk about it in the class. Right, and then time constant for all three axes is minus 1 over 50. So the time constant gets shorter when I have more damping. We talked last time about how that's sort of counterintuitive. The aircraft is actually faster. And things happen faster even before that. I have a lower steady rate when I do that faster. And then the original acceleration, or the acceleration at time 0, is sensitivity times input time. really not. Okay. So, getting now, let's talk about the time constants. And we talked about all the three different dampings. There was MQ, LP, and R. And what we said is probably roll for a single main rotor helicopter was floating at 76 inches. This is the biggest absolute value damping because using the main rotor impact plane lag, which is, for Blackhawk, that's a 16,800-pound vector, and offset if you have it, which the S-76 does have, and really low inertia. Right? And so it's got a big damping moment generator and low inertia. This has a big damping moment generator, but a lot more inertia than rolling. This one only uses the tail rotor and has a bunch of inertia. So this is usually the smallest absolute value. Biggest absolute value, medium. Right? And so, in most of them, both cases, in all three cases do the inertia, and then, pitch and roll like that main rotor. So then it's 1 over. So the longest time constant is going to be 1. And the shortest time constant is going to be 1. How will the time constants with a half-inch input compared to 1 inch? Input size does not matter for that. As long as everything's turned off, so I don't have sashes saturated or anything. It's a linear, for a half-inch and an inch input. It's probably a good assumption to say that we're still kind of in a linear input. With no nonlinear things happening. The time constant is not a functional difference. So I do 1 inch input, I'll get the same time constant as 2 inches. That works out. How would steady-state rates compare to the SAS on dating collected the other day? Well, what does the SAS do? SAS is, in all three axes, fire the cells onto the aircraft by increasing damping with the 1 and 1 watts. And it can do other things what would happen here on the aircraft. And so in all three cases with the SAS on, this goes up in absolute value. All these go up. The negative numbers are going to go up in absolute value. So the steady-state rate will be lower, which is also sort of counterintuitive. And that is, with the SAS on, I actually get less rainfall given input. Less temperature. Which leads to part D, which may not be, what I just said here may not be as true as what we said. Right? And it says, if the SAS saturates the remaining responses, how will your data be affected? Okay, so picture, we had, let's say, just pick the roll axis. All three axes are working. And excellent tool line. Where I have delta 10, I do a step to delta 10. Right, the range I'm going to look at, strip out, if I have an instrument, delta SAS. Then I'm going to have theta tail root. Using the garden, and then I'm going to have delta. Right, and this could just be the delta lat, delta SAS, and roll, big A1S, and roll. And it just easily be delta log, delta SAS, and finish, big D1S. And so I do step smaller. What happens is, as soon as I do the step, I get R dot at 0, so I get an acceleration in the eye. So I do the step input, the aircraft takes off to the right. And so that would happen at the same tailwind in the back. So these are opposite this actually. Right? And so then, as the rate comes on, the SAS is designed to oppose to it. Right? And so, because a good damper would be, if I get a right yaw ring, I would have a left yaw moment counter. Right? And the tail rotor, if the SAS turned off, the main source of damping is tail rotor is living as local from the rate, and it takes away blade pitch and naturally reduces each blade on the angle down. If that's not enough, what I'll do is I'll actually feed in more pedals to oppose the blade. So So what will happen is, this SAS will oppose the right geometry come on like this. Okay, so until such time that I'll reach some steady state rate which will be lower. Okay? And it'll take some ranges away. In other words, this isn't the scale. This piece right here is how much the SAS took away. I put this in as time. So the tailor length has changed. Then the rate came on and the SAS took some out of it, which to the aircraft feels like, in this case, tailor length is to oppose the rate. Okay, so here's the SAS. Okay, now, let's say I do a bigger one. Okay. What is the units on, a good unit on SAS feedback gauge will be for a given rate that's coming on in degrees per second. Okay. The SAS, let's say this is a percent. For a given rate, it's going to oppose it by a certain amount. So let's say that number is 1, which the units on will be 1% per degree per second. And let's say the SAS has 10% of fluid. Can't then get rid of them. So if my gain is 1% per degree per second at 10 degrees per second rate, and if this thing comes up to 10, this thing will saturate. On that big input, that's big input, that's more than I did some big, right? Yeah, bigger input. So for the big input, the SAS will eventually saturate at some point because the dollar rate will reach that amount, and then in our case was 10. At 10 degrees per second, it's out of switch. And at that point, the aircraft goes back to their flying point, SAS off flying point. Because now the SAS is too flat. It can't oppose any more rate, but the rate's not done going. And so, at this point right here, where the rate starts, it'll pick up some different profile, probably some longer time curve. This thing was about to be done in steady state. But at this point right here, it picks up the SAS off damping amount. The SAS off damping amount, which is going to make kind of the remaining piece of the response have a much longer time constant. Because the SAS is off and I don't have the advantage of it's too long. So I don't have the advantage of that. Okay, now, to a designer then, right? Is this necessarily that? Now there's kind of two things in the design to trade off. One is, we made up that number of 1% per degree per second. That's the amount of augmentation that I have. And the bigger that number is, the more augmentation. So that's fairly straight. But then, if I said, okay, I'm going to change that number to 2% per degree per second, this thing will saturate at 5 degrees per second. So the rate at which the SAS saturates is something they can also design by trading off how much gain and then how much authority I'm going to be able to make more authority or something. So it doesn't saturate. Imagine if you had a SAS saturated at like 2 degrees per second of the algorithm. So I get a rate going, and at 2 degrees per second, it switches over to a different health. And in most cases, it works. They wouldn't have spent all the money on that SAS if it was better. Right? So once the SAS saturates, I'm back to the fair aircraft. If that happens at a low enough rate, then that would be very unpredictable spot. For a little bit, it makes one predictability. Then for a little bit bigger rate, it takes off, and that's twice the steady state rate or something like that. So it can be too low. And then the ideal thing would be to make it to where once it saturates, design the system to be such that once it saturates, I'm at a rate high enough that I don't notice it. But I care about this dancing right here, really, really short time constants. I care about that when I'm trying to speak things at the last second. But stop precisely on heading, or if I'm pitching, okay, all this 5 cylinder gas. If I got a rate going in pitch, I want to stop on the target. That stopping on the target thing usually happens when rates are really low. Okay, And so, as the rates come down, like if I take the input out or something, right, the rates come down, this will come off the saturation. That gives me a nice short time constant, nice quick return. And so I get the best of both worlds. I can get the precision that comes from short time constants for low rates. And once I'm into big rates, this thing rocks up at some value, and I can still generate big steady state. So if I do it right, I can get the best of both worlds. I can command big pitch rates, big roll rates, and big yaw rates, because once I get above a number like 10, once I get above a certain number, that thing saturates, and it's not opposing rate anymore after the aircraft. Right? And so when I'm doing a big high active pitch maneuver, a big rolling maneuver, I'm going to shoot my precision. Until I get ready to stop it, then the SAS comes off of the saturation and helps me out at the very end. So we kind of get the most best possible. Okay. So that's a pretty long answer to part B. Just once you get moving. How will that affect you, Dave? Correct. How would you handle it? So the next one is on the test techniques, which we're going to definitely be done with those this week. Technical scientists and all that. Okay, so on the home stretch of going through the equations and looking at derivatives, we're only left with the sine force equations. Forces in the y-axis. So we did talk about L delta last time, the left hook and the A point zero and all that. L delta fed is pretty straightforward. That's because of how it goes. If I step on the pedal and I have a high tail where I have